Now, if we come to the gyroscope proper, here is an example of a mechanical gyroscope consisting of a rotor in two frames. The rotor can be spun. We'll spin it in a minute. One frame can turn that way. One frame can turn that way. So the axis could actually point anywhere in space. So now if we drive that up in speed, we can see that we'll get extreme stability and also a peculiar motion called precession. Mr. Jameson will drive it up. Now, it's spinning away quite happily, and it really is quite stable. As you can see, if I give the outer gimbal quite a sizable tap with a hammer, then it moves very little. This is waggling at the end, but that's just the flexibility. So it's really quite stable. Moreover, if I push in this direction down here, you see the axis moves in quite the other way at right angles. And that's the so-called precessional movement. It's really fairly simple to understand, provided the motion is steady. What happens is this angular momentum vector, it's the vector associated with the spin about that axis, moves in the direction of the torque vector. The torque vector, if I push down there, points in that direction, i.e. about that axis. And so it will move the angular momentum in the direction of the torque. That is, the torque is the rate of change of the angular momentum vector. So it's quite easy to remember those directions if you think of these arrows, one for torque, one for angular momentum, and away she goes. Now the slide shows a device that was invented about the turn of the century by an inventor in this country for a two-wheel car. And those four Edwardian gentlemen are actually sitting on top of a large wheel inside the body of the car in that sort of configuration, keeping the car stable on two wheels. It was never successful, although in fact it was technically quite adequate, and the car was driven from London to Birmingham and back several times, I believe, but it never caught on with the public's approval, and instead two-wheel vehicles of a rather different kind, motorbikes and bicycles. But it was an interesting technical idea. Now, the next gyroscope we'll show you, I think, will be the top, or perhaps the tightrope. Let's do the tightrope if we can get that started up. Demonstrating a stability of a similar kind. Do you mind to hold that? Good. This is a two-wheeled vehicle, if you like, and we'll start it off with the wheels balanced rather precariously, up a little bit, Bill, and it will, with any luck, stay there, but run down the tightrope. And there she goes. It wasn't quite on the wheels, so we'll put that back in that position, and now it should be all right. And it goes right down to the other side, and we can run it backwards by dropping the far end. And again, it runs down in quite a stable way. Similar to the Shklovsky car, in fact. And finally, the very familiar kind of toy, or at least it was once familiar, the top. And here we can produce the action of two tops, one on top of the other. And this illustrates precession. And you see, we could keep on building up like that, and it really remains very stable, and it's a very nice thing to watch. Fine. Thank you, Alan. Good. Now, as I mentioned, the gyroscope is not simply a toy, and we have one or two examples of the ways in which it can be used to stabilize objects in practice. This, for example, is a real momentum wheel, as it's called, used in British aerospace satellites. It would take us too far afield to explain precisely how it works, but it acts somewhat like a gyroscope. It's carried in the body of the satellite, and by virtue of its stability in spin, that it confers a degree of stability upon the satellite. It's very carefully controlled, and as you can see, it's rather a beautifully made wheel.